Okay, if not, then maybe we hand over to Paul. So maybe you want to give him applause to welcome Paul.
I'll stand here.
So I want to quickly introduce Paul. Paul is one of our seniors in the team. He has a PhD, he has industrial research experience. He comes from one of the big tech companies, and he took over this really complex problem of consensus, and he will talk today about the new consensus protocol. Please go ahead, Paul.
Thanks very much, Bernard, and thanks everyone for coming. Okay, so I'll talk about the consensus. Bernard briefly mentioned how it fits into the client architecture. I'm going to zoom in a little bit and tell you how it works. Okay, so the consensus problem is really, you can view it as keeping the blockchain as a replicating computation, or as in theory they call it a replicating state machine. So this could be seen as a kind of a computer from the outside that accepts transactions as inputs from different clients, and each of the nodes within this computer independently want to replicate the state of the blockchain. And this is really important because if you have inconsistent state, you can have attacks like double spending, and we want the ledger to remain consistent as well. So the consensus problem is really about keeping all these different nodes consistent during this computation. Now, this has to be done also when we have faults happening. So a computer could go down, and we can't just have the blockchain stop working. We need it to continue working. What makes blockchains even more interesting is that we also have to account for nefarious actors, so-called Byzantine nodes. And in the literature previously, this was seen as maybe a software error, but as you know, in the blockchain world, this is usually some kind of hacker trying to exploit the network for financial gain. So even with these happening, we still need this consistency. And so this is the theoretical problem. It's been studied in the 1980s. And what I think is particularly interesting is that this actually, unless you make some assumptions, is impossible. And that might be quite news to some people, but this comes from the famous FLP impossibility theorem. And it says, if we have a deterministic algorithm, that's our consensus algorithm, and we don't assume anything about timing, all we need is one of the nodes to crash, and we can't solve the problem. We can't have that consistency. And what this means practically for us is that we have to make some design decisions. And we have to choose between timing decisions, the determinism of the algorithm, and the termination of the algorithm. And every protocol has to make this decision. And what we've done in our protocol is really focus on the determinism and the asynchrony, because the way we've done it, it's very unlikely that it won't terminate. However, we can make different assumptions about the network timing, and then we can ensure termination as well. So the protocol we use is called a DAG-based protocol. Here we have units of transactions we call events. Each of these have a hash, and they have parent hashes. So they actually link up to previous events that have been seen before by that node. And the idea is that you can create these events and you disseminate them. And everyone disseminates them amongst each other. And eventually we form what Bernard mentioned, this directed acyclic graph. So it's a graph of connected events, and each of these events contains transactions. And the idea is to find these synchronization points so we can create blocks, as you see above. And we call this linearization. What's interesting is because we have an asynchronous network, that things can lag, and that's fine. But they'll always be consistent. There'll never be inconsistencies. And eventually, the lagging nodes will catch up, assuming we have some finite tax or delays. And the main advantage of this approach compared to other protocols that use what they call leader-based techniques is we have much better utilization. So in other protocols, you typically have one node that's a leader and it's sending out all the information to the others, and the others are just kind of sending acknowledgements or votes. Here, everyone is kind of a leader. So we don't cap the utilization by one node. We actually keep things evenly distributed, and therefore we get much better throughput and performance. So not to go too technical, but the main operation we have is what we call strongly reachable. And the idea is we go from one event. We initially have the first events as special, what we call base events. And when we see that another event can go through a quorum of validators and it doesn't see any forks or equivocations, we can say that this event strongly reaches these previous events. And we use this to layer the DAG into several layers, and these layers form the basis of our election, which we'll look at next. And in the election, we first have a round of voting. So here we want to vote for one of these synchronization events in frame 2. We already have one in frame 1. And the idea is using this operation, if it can reach this with that reachability characteristic, we can vote yes or no. Okay, so here we vote yes several times. And then we have some aggregation that counts these, right? And the idea is when we can elect several of them, and then when we pick one in a particular manner, we can then do the linearization, which we see here. And all this means is we collate all the transactions and we form a block according to some topological order. Now, the naive way of doing this is in a sequential way. So we go, okay, we're doing an election for frame 1, and we keep doing this until we're finished with that. And then when we're finished with that, we start all over again, okay? So then we try and do this for frame 2. And what we notice is this is quite inefficient. We can do much better. And instead, what we're going to do is do several of these elections at the same time, and they'll overlap. You can view it as, if you've studied computer architecture, like a processor which pipelines things, right? So we're doing a sort of pipelining, and we're going to conduct several of these elections all at once, and this makes things a lot faster. So yeah, when we get a base event, it won't just cast a vote for a particular frame which we're trying to decide. It may also do some aggregation as well, and choose an atropos, choose a leader if possible. So we cast events we cast votes, like I explained, using the strongly reachable operator. If it can, we say yes. If it can't, we say no. And then we do the aggregation. Now, what's interesting is that if there's any previous votes that occurred, they remain materialized. And so when the next event comes in, we can actually use that to actually try and make a decision. And that's what happens here. We can actually perform the voting ahead of time for this frame, which will eventually come to an election, but which will eventually have a decided election. But at the same time, we can aggregate and try and decide as soon as it's there. And as you see, we can then have a decision for this next frame. Now, what's really interesting is we can view this as a set of matrices. So every base event, the votes can form a matrix, and where +1 or -1 is either a yes or no. And what's interesting is that by using some mathematics, we can do this aggregation inductively. And we can make a decision based on these metrics. And the rule is if something of high stake hasn't been decided, we still wait for it, right? But if it's decided that it can't be a synchronization point, then we can decide to do that. And this nice formula describes this in detail. I think we described this in the blog post. And because we're using matrices, we can actually parallelize things. So we can actually, instead of performing things for one unit at a time, we can do the operations on rows in the matrix. And this speeds things up considerably. And here we can see the experimental evaluation. So we took the previous protocol here, and this is our new implementation. And we have a speed up of maximum of 2.62 times, which is quite considerable. And on average, we are 2 times faster. And the main thing is that we never are slower than the previous one. So that's, we think, very beneficial. And what's even more interesting is that we don't only get a speed improvement, we get a memory reduction. So here we can see for each of the phases, we have frame building and the election phase. And overall, we get 67.8, so we're under to 70% memory reduction for the entire consensus. So that's quite a big deal, and it'll improve the space needed. So the future, we are going to implement this pipelining vectorization consensus in production soon. And we're already working with more improvements that are on the way. So we're going to keep you updated with that via the blog, as we've previously done on X. So stay tuned. And yes, that's all. Thank you very much.
Are there any questions for Paul?
First of all, thank you for the presentation. My question is very simple. Is there a reason why the Sonic team decided to use the SMID and not the MIMD? Because I'm pretty sure there are multiple ways to increase branch predictability. And yeah, I was just wondering why did the team go for SIMD?
I think that the nature of the algorithm is such that we can exploit one operation for multiple data. So that's what our reasoning was.
Are there more questions?
A simpler question. Thank you. I was wondering if this, if the consensus part is what is already in production on the current Sonic mainnet, or if it's for the new update that's coming in a couple of months.
Yeah, it's from a new update. So this
okay,
is,
thank you.
yeah.
Okay.
Just to say, we have next upgrade of Sonic will be Pectra, and the following upgrade will be the new Sonic consensus protocol. So it's not the next, but the one after the next.
Hey, I just wanted to ask what the major differences between Lachesis and this protocol are.
So not to go into too many details, but the main difference is the overlapping elections and also the matrix semantics. So I would say they're the major ones. But there are some other ones that are a bit more low-level technical. Yeah.
Thank you.
Do we have more questions? If not, let's thank the speaker.
Thank you very much.